Hello and welcome to Tvaritam.AI. In this video, we are going to understand logistic regression. Logistic regression, despite its name, is actually used for classification problems. Instead of predicting a number, we predict a probability between 0 and 1 and then use that to decide the class. To understand the mathematical intuition behind logistic regression, we will start with a linear equation. As in linear regression, our output is equal to the weighted sum of inputs plus the bias term B. But this output can be anything from negative infinity to positive infinity, and our probability must be between 0 and 1. So we need a way to compress this range. For this we use a sigmoid function. Our predicted probability is the linear output we calculated passed through a sigmoid function. Now when any input is passed through the sigmoid function as shown in the graph on the right, if input is very large positive value tending to infinity, output becomes close to 1 or approximately equal to 1. If input is a very large negative value, the output becomes very close or approximately equal to 0. And if the input is 0, output is 0.5. So it smoothly converts any number into a probability and makes a linear model a probabilistic classifier. Now for decision making, once we get probability, if the value of P is greater than equal to 0.5, the row belongs to the class label 1. If it is less than 0.5, then the output is class 0. This threshold can be adjusted depending on the type of problem. So we can also make it 0.6 or 0.4 as we desire. Now for multi-class classification, where we have more than 2 classes in our output label, we will use a softmax function instead of sigmoid. Using sigmoid for each class separately does not give a proper probability distribution, and the sum of probability may not be equal to 1. A softmax function output multiple probabilities across all classes with sum of values being 1. For example, values such as 2, 1 and 0.1 when passed through a sigmoid function will give 0.66, 0.24 and 0.1 as the respective probabilities. For 3 classes, the formula to calculate probability for the first output looks like this. For second and third output, we need to change the numerator term. So we can make numerator e raised to the power z2 or z3. Here it is also important for us to note that the input to the softmax functions z1, z2 that you see are not the raw features. They are the final scores or the logits from the linear model for each class. So this is the prediction from the linear model and not your input variables. And here we use exponent to make all values positive and amplify larger scores. So the model becomes more confident. We could also try other transformations, but softmax with exponent is usually a standard because it works well mathematically, especially for optimization. Now let us talk about loss function for logistic regression. Loss function is used to measure how much the prediction disagrees from the true label. In case of classification, we want small loss when prediction is correct, large loss when prediction is wrong, and a very large loss when model is confidently wrong. So for binary classification, we use binary cross entropy or log loss. It helps us to punish wrong predictions non-linearly. And for case 1, as you see, this formula negative of y log p plus 1 minus y log 1 minus p becomes minus log p negative of log p if the true label is 1, because in this case this term will become 0 and second term will become irrelevant. And in case when true label is 0, then the first term becomes 0 because y is 0 and we are left with negative of log 1 minus p because this becomes 1 minus 0. Right. And as log values for input less than 1 is negative and probabilities will always be less than 1, we add a negative sign in our formula here, and this makes optimization easier as we minimize the positive loss. Now to understand a little bit with an example, if we have a true label equal to 1 and in case 1 our predicted probability by the model equals 0.9 and the loss is negative log of the given probability, predicted probability, that is 0.9, and we get a 0.105 as our value for the loss. But in case that the true label was 1 and model predicted 0.2, the loss is much heavier and we get a approximate value of 1.609 for the negative log of 0.2. So this makes the penalty heavier for making confidently wrong predictions. When it comes to multi-class classification problems, we use categorical cross entropy. It works with softmax where probabilities sum up to 1, and in most of the cases when only one class is correct, the loss function reduces to this, because this yi for all the classes which have 0 will automatically make them null. So to understand a little bit more, let us assume that we have a 3-class classification problem A, B, C, and in this particular case true label is B, and when we one hot encode the target, it is 1 for B and other values are 0. Now for case 1 where predicted probabilities look like this, because for A and C the values are 0, the yi is 0 and they will not contribute towards calculating the loss. The loss would be minus or negative log of P for the correct class, in this case B, and we have a value of 0.9. So our loss is a very small value, that is approximately 0.105. For case 2 where we have a bad prediction and the predicted probability for our correct class was 0.2, we get a negative log of 0.2, and now the loss function is a much higher value, that is approximately 1.609. In case of a very bad or confidently wrong prediction where the predicted probability for the correct class is 0.03, the loss again is approximately equal to 3.51, and that is how confidently wrong predictions will get a much higher value for the loss. Now concepts in logistic regression like optimization, convergence and regularization follow the same underlying principles as we have discussed in the linear regression. The only key difference lies in what we optimize. Instead of minimizing the squared error, logistic regression minimizes the log loss to better model probabilities. So if you want to understand how convergence, regularization or optimization works in logistic regression, you can refer to the linear regression video, and those same principles can be applied here also. Thank you.